Hi everybody, my name is Alex and I'm going to present to you today about Lushu, which is my dissertation for the bachelor's degree program in computer science in UFMG. Lushu is a tool to obfuscate sensitive data automatically, and it does that through language recognition. So first, motivation why Lushu exists. Originally was because we wanted to obfuscate sensitive data automatically without having to know much about the program. And this is also backed up by data protection laws that were recently created that require that you have extra care with sensitive data. Like, you need to be as careful as possible to not mishandle the data. And these data protection laws were created after most of the systems that are in production today were already in production. So you can't just expect the companies to completely rewrite the whole program to meet the data protection laws. It would be better if you had something that treats them as a black box and just doesn't need reprogramming of the whole program. And the second benefit of Lushu is that it's extensible. So we recognize the language of the logs, and you can do whatever you want with that, including but not limited to obfuscating the sensitive data there. And this is the context we're in. We have the log producer to the left here, produces a log. We recognize the language with a grammar. And then with that grammar in hand, we can encrypt the sensitive data because we know where it is. And so from here on, everything is encrypted. So the administrator can only see the encrypted log. But somebody with the encryption key, which supposedly this person needs to see the encrypted logs for auditing. That person can have the encryption key and then, of course, he can decrypt the sensitive data. So, for example, here at the bottom, you see the original log and the encrypted log. So the IP addresses are obfuscated. And we do this by intercepting output calls to system.out in the JVM, Java Virtual Machine. And those logs are intercepted and go to the Lushu learner, which learns a grammar. And there are two other inputs that need to go to the Lushu learner, not only the log, but also user inputs. So the user, so it can be a programmer, an administrator, or whoever, needs to define via markup language, which is similar to XML, we're going to explain in a bit, where the sensitive data is in some example logs, and also a set of regular expressions that we can expect to see in those logs. And of course, finally, we encrypt the data. So this is the first thing the user needs to define. You see at the bottom left here, there are a couple of sets, character sets. So for example, the alpha set is a set of lowercase letters, and it can happen anywhere from 1 to 8 times in token. And the alpha with uppercase A is the uppercase H to Z, uppercase alphabet letters. And it can also happen from 1 to 8 times. And so the user specifies these things, and from here we build this whole lattice here. And this lattice is the main idea of this work, to reduce or compress the tokens into something more compact. So for example, instead of just saying that it's the number 2, we're going to say that it's a digit. And the lattice goes from less complex at the bottom to more complex at the top. It's a semi-lattice, a join semi-lattice, and the join operator is simply character union. So the second thing that the user needs to specify is where the sensitive data is. So in this example, the user specifies this sensitive token, this one, and this one. And from there, we can, if we get this log at the JVM and Lushu is running, we're going to be able to encrypt the places where the user specified those formats. So at the last word here, we are able to encrypt IP addresses. And the third word, we are able to encrypt this other format here. But you can see that the second word in this third log at the bottom here is not encrypted, even though it's an IP address. That's because the user did not mark this position as a sensitive IP address. Okay, so we're going now into like explaining how Lushu works to do that. So we use that lattice of regular expressions. You can see here the regular expressions, and we're going to split the sentence into multiple tokens. So this sentence has 4 words, but it's split into 6 tokens. That's because the second word contains a semicolon, which we cannot merge with a digit according to the user specification back here. So you can see this widen block. This says that we need to go to the lattice top when we see a punctuation. So we cannot merge 1 in semicolon, we cannot merge 10 in semicolon. So this becomes 3 tokens, this word. And at the end, we're gonna say that the first word is a digit 4 times, the second word is a digit from 1 to 2 times, the second token, sorry, and so on. It can be a little bit more complex. It can be anything in that lattice. So for example, it can be the unit of lowercase, uppercase letters and digits. So here from 2 to 3 times, because it encapsulates the number 0, 5, and also the word may with uppercase M. After splitting the sentence into tokens, what we do is we build the grammar to the right here. Sorry, there's a lot of things in this slide, but so A here is the example. B is a trivial grammar we built first. C is the predecessor tool, and D is what we do currently in Lushu. So essentially we jump from B to D. And Lushu and the predecessor tool did something in between where it was just able to merge the integer and floating point numbers into a common pattern. So for example, rule 2 here, instead of being both tokens, it's just going to be 1, which is the integer token. But as you can see in the D item here, item D, the Lushu grammar is much more expressive in terms of it tells us much more about what the logs actually are. And it's much more compact than the Zhefuscator grammar. We're going to talk about that later. So, and this is the grammar that we use for language recognition. This is it. This is called the heap CNF grammar. And this is how we construct it. It's essentially a heap of Chomsky normal form grammar. I'm not going to go into details here, but this is how we construct that. And lastly, so we evaluated Lushu against a couple of benchmarks. First, like you've got to ask yourself how big of an impact Lushu has on real programs. If you put Lushu in your program, is it not going to make it too slow to be usable? And the answer is it's not going to be too slow. So for instance here, we're running programs that only print logs, and we can see that in the gray and blue lines here, that the cost is linear, so it's constant per log. And also it only becomes a big difference after like 1,000 logs in a row. So most programs are not going to print 1,000 logs in a row. They're going to be doing other things too. So only if you print like 1 million or 100,000 logs in a row non-stop is that you're going to notice Lushu. Otherwise, it's not going to notice it in terms of execution time. Also in terms of memory, it's constant. So you can see here the black line is without Lushu, the green line is without Lushu, and the 2 lines above here are with Lushu. And there's just like a 2 megabyte difference. And this is for very lightweight programs. So if you have a program that already consumes like 100 megabytes, 2 megabytes is not going to be any difference at all. And you can see that it's constant from 1 to 1 million logs. It only grows 2%. So this is a constant memory use because the grammar converges to a constant size very quickly. And finally, a comparison with the previous tool. The previous tool was called Zhefuscator. It did basically what Lushu does, but with a worse grammar. So the language recognition was worse. It was not able to merge tokens into regular expression like we do. And you can see here that the grammar Lushu produces converges very quickly, and it's much smaller than the Zhefuscator grammar. So when we reach 2,000 logs at this point, our grammar is about 10 times smaller than the Zhefuscator grammar. So it's much smaller. And this is the main contribution of our work compared to the previous one. And that's it. Thanks, and special thanks to Professor Fernando for all the help from the beginning to the end.